Cool. All right. Good afternoon, everyone. My name is Siva. Hope everyone had a great lunch. I'll be talking about the next section of this tutorial, which is vehicle-to-vehicle communication. So I think in the previous section of the tutorial, we covered several of the components of an autonomy system. And one of those components was perception, and in the modular-based autonomy system. And to recap, for a perception module, you have the assumption that you have a single ego vehicle equipped with a set of sensors, such as cameras and lidars. This sensor data is then processed by the autonomy system. And if you have an interpretable system, you can generate outputs of the perception system, such as detection, bounding boxes, and trajectories for motion forecasting, which are then used to perform motion planning. And in the previous talk, we've done a lot of, like Ewan gave a great overview about the perception system, several of the enhancements that have been done in training and architecture. But there are still a few limitations with making the assumption that you have a single ego vehicle that is processing the sensor data from a single viewpoint. So, for example, in this situation, we have a single ego vehicle here, single simple lidar point cloud. And for very dense nearby regions, such as that vehicle here, we can see we get a very good, confident reading of what is the shape of the vehicle, where it's going maybe, and what class it is. So for dense regions, no problem with single vehicle perception. But maybe for faraway regions, we have very sparse point cloud, for example, or very far away, the image, the cropped region of the actor is very small. It's hard to tell what class it might be, how fast it's moving, where it might go. So this might be the situation where we can't get much of that information, even with training and model improvements, to see what's happening for that actor far away. And similarly, if you only have a single ego vehicle, you can only view from a single viewpoint. And by doing so, you have occlusion. So you can't really see in a lot of these regions that are missing what's actually happening in the scene. And for both the faraway regions and for areas with occlusion, in most cases, this doesn't affect autonomy performance that much. Most of the time, the actors of interest are just nearby actors. But in certain situations and long tail scenarios, it matters quite a deal what's going to happen to those fast moving actors far away that might turn into your lane, or something that comes out of occlusion very abruptly. Being able to detect them in time might make a difference in safety and comfort of the drive. So in this section of the talk, we're going to consider a different scenario where maybe in the future, we have much more self-driving vehicles in the scene, in the same vicinity. Maybe there's also some infrastructure available which has sensors equipped with it. And the premise is that, maybe in this future situation where there are more self-driving vehicles, they can each collect sensor data about what they see in the world, and they can communicate that as messages to the ego vehicle. This ego vehicle can then process this sensor data and have better perception about the scene. We can see around the occlusion because we have more visibility from the different viewpoints. And we might have vehicles that are closer to the faraway regions for that ego vehicle in particular. And this allows for better perception in theory. So to recap, the benefits we might see from vehicle-to-vehicle communication, or V2V, and vehicle-to-infrastructure communication, V2X, might be that we can see better through occlusions, we can see better faraway regions, and we might have more evidence about different things we already see for overlapping fields of view. And the other benefit is that typically these sensors are equipped on infrastructure or other intelligent vehicles. They'll have compute available. So we can run perception processing on this data ahead of time. And it allows for distributed network computation for still having fast real-time speed of a safety critical system. So these are the benefits of the vehicle-to-vehicle communication setup. But as we'll see in this talk, we're going to be going on several related works in vehicle-to-vehicle communication. And there's several open questions that remain in the field that the people have been trying to tackle. So for example, what information should we be transmitting about the scene from one vehicle to the other as messages? How do we aggregate this information together, fusing different sensor data and whatnot? And in particular, how do we support heterogeneous sensors, vehicle platforms, perception models? We might assume in the future that there might be different autonomous driving companies available deploying their vehicles. How do we handle different architectures having different generations of perception outputs? Maybe we have cars and self-driving trucks, vehicle infrastructure. Each of these sensors have different fields of view and calibration. How do we fuse this data together? Additionally, this is a safety critical system, self-driving vehicles. They need to operate in real time. When your data comes in, makes a huge difference for how you can perceive what's going to happen in the scene. So how do we make sure that these messages that we transmit are not too bulky? We can make it fast enough so that these vehicles can still perceive in time as if they were still a single vehicle doing perception with their own set of sensors. And then finally, when you introduce the notion of vehicle-to-vehicle communication, what other vulnerabilities do you introduce in such a setup? Because when you have something coming into your set technology, there's always something that arises you have to handle appropriately. We'll talk about that as well. Cool. And I'm going to go over some past works in vehicle-to-vehicle communication, and we're primarily going to categorize them by the first question: what information should be transmitted? Because by answering that question, that can affect how we answer the remaining questions. So to answer the first question, what type of strategy should we use for transmission for vehicle-to-vehicle communication? So one option is to transmit the raw sensor data itself. The other is to make autonomy run its perception module and generate perception or prediction outputs and communicate that instead. And the other is to potentially transmit other intermediate representations. And I think in UN section for the perception tutorial, we covered this idea of multi-sensor fusion, and some of the same type of problems that are encountered in multi-sensor fusion we'll see come up again in this type of information to transmit. You can think of early fusion, late fusion, and mixed intermediate fusion as the same type of notion here for vehicle-to-vehicle communication. So in the first situation, one option is to transmit the raw sensor data. So in this example here, we have LiDAR point clouds that are being captured by different vehicles in the same vicinity. And for LiDAR point clouds, it's pretty straightforward. You have the relative pose that you can transmit between the different vehicles, and you can aggregate the point clouds in a shared coordinate space and then perform perception, prediction, and so on. And the benefit of doing this type of aggregation of the point clouds is you have no information loss. And also it's very simple to combine, in this case for LiDAR. For other sensor modalities such as camera, you need some notion of correspondences or depth to be able to put them into a shared coordinate space. Now, some of the downsides of this approach is that you can imagine if you have, say, a vehicle with, say, 5 LiDAR sensors and there are 5 other vehicles in the scene, the amount of points that you have to process becomes huge. So it's going to take a large amount of time to send those point clouds to the ego vehicle, and it take a lot of amount of time to process those point clouds. Additionally, sensor point clouds have noise or other sensor modalities as well. And when you just simply naively aggregate them in this situation, you can aggregate noise and have also redundant information about the scene that is maybe not necessary for certain overlapping fields of view. And in the naive aggregation case, maybe there might be future works that handle viewpoint aware aggregation of point clouds or sensor data, but in past works, typically what people will aggregate, they lose information about how each vehicle perceived the point cloud or camera data in the first place when you fused. And that might affect how you want to handle that sensor data for performing autonomy. Now, on the other side of the spectrum, you can perform communication of the perception and prediction outputs. So here we have each autonomy module of the self-driving vehicles performing perception on the LiDAR point cloud. You get detection bounding boxes, and you simply communicate the bounding boxes or trajectories if you also do motion forecasting between the different vehicles, and then you merge them all together in a greedy manner. So this is the naive type of output fusion approach. This is very compact. You're only sending a very sparse representation of the boxes and the trajectories. The other benefit is that if you assume that most people are doing modular-based autonomy systems, you can standardize the format of, I'm all going to output the same type of representation of bounding boxes and trajectories, or maybe everyone assumes we're going to output occupancy maps, and you have ability to communicate a shared representation that works across different platforms and different infrastructure. And the other benefit is that you run the full perception system. So you do the full distributed computation required to get what's required for prediction and planning, or whatever components, how you break up the autonomy system. But the downside is that when you do this type of perception, in the case for detection, object detection, you do thresholding. So you kind of lose all the scene context of what's going to happen from your sensor data and just say, here are the actors in the scene. So you have also limited expressiveness because you can't really convey uncertainty about, oh, I'm not certain about this particular region, or maybe I'm very confident about one other region. And because of that, and the thresholding for at least detection that uses bounding boxes as the output representation, you are prone to more false positives potentially. So this is kind of the simple version of output fusion. And there have been several works that try to kind of address some of those limitations. So one thing I mentioned was that you lose scene context when you output just bounding boxes and trajectories. So one recent work tries to kind of do the best of both worlds of combining both LiDAR fusion or sensor data fusion with output fusion. The kind of premise here is that maybe for regions as a potential intelligent vehicle, nearby regions, I'm very confident my observations of what the actors are doing, So I can just say here, I know where the vehicles are. I know how fast they're moving. I'll send just the detection bounding box as a sparse representation for very nearby scene areas. But for more faraway regions, I might only see one side of the vehicle and I might not know much about what is happening. I'll send that partial point cloud of that faraway actor to the rest of the vehicles in my network. So you kind of get the best of both worlds. You have to balance this trade-off between what information you transmit of the point cloud data or camera data, or do I output the actual bounding boxes and trajectories? And this allows you for areas where you're more confident, you send something more compact. Areas you're less confident in, you send more information about that area. And the other thing I mentioned for output fusion was that you can have a standardized format of detection bounding boxes that all the companies produce that you can share between the different vehicles for vehicle-to-vehicle communication. And in this particular work, they handle one of the caveats with that, which is that different perception networks might output different types of confidences associated with those bounding boxes. So maybe you train a particular network on one data set with, say, point pillars, you output certain confidences associated with it. And then maybe another network such as second, you output some certain confidences with it. And they're not very calibrated across different autonomy systems. So this approach tries to calibrate those confidences and then try to more intelligently fuse bounding boxes with overlap to allow for a better, more intelligent fusion of output data. So we talked about input fusion of the sensor data, output fusion of the perception prediction outputs, assuming a modular-based autonomy system. And the third approach we'll talk about is intermediate representations. So the premise here is that you have neural networks that are processing your sensor data. You can generate intermediate feature representations that you can fuse between the different vehicles. So the benefit of feature maps or learned kind of like messages that you send between the different vehicles is this: you can be compact and expressive about what you're sending because you identify what's important for the task, in this case, autonomy, and you send only that information about the scene. You can also get your viewpoint preserved because typically when you send these messages, you can also encode, hey, this is the pose I'm viewing the sensor data from, and here's the timestamp I observed it. So it's easier to fuse it more intelligently, potentially. And again, you still have the distributed computation, but maybe you need to do a bit more processing work and fusion between feature maps compared to the perception prediction outputs than we talked about output fusion. But the one downside is that if you assume that there might be like heterogeneous autonomy systems out there in the world, you have to do some type of domain adaptation if each autonomy system is performing their own sensor data processing. So there are several types of features that could be used for transmitting intermediate representations. We outlined a few here. You can use voxels, point features, image features, bird's eye view features. The main premise is that you need to have some type of shared coordinate space or spatial representation maybe to communicate messages from different points of view. That's kind of what all of these have, but they each have their own kind of assumptions and whatnot, but that's kind of the premise. And then for intermediate representations, there's not just what you send, but how you actually fuse them together. And so there are several works in the field from the past few years that we showcase here. You can use graph neural networks, adaptive feature fusion, and transformers for kind of sending messages and fusing them together intelligently as best as possible. And as I mentioned before, each of these messages, you can associate metadata with them, like the pose of where the message is being sent from and the timestamp. This can help because like these are self-driving systems that are constantly getting new sensor data and performing autonomy, and they're not synchronized with each other. So it's important to tell like, here's where I saw this particular information at this time. And then the network can kind of reason about, okay, based on this timestamp, this observation, I know where it's going to happen next. And it's better to kind of merge the sensor data together. Cool. And then there's a couple of enhancements that people have worked on for intermediate fusion. So one approach that this paper proposes is applying kind of this notion that maybe intermediate fusion, you're only getting feature maps, but I may not know how to merge those feature maps together as best as possible. So what they propose is say, offline, they have a teacher network that processes the raw sensor data in the assumption that you have infinite time and compute to kind of, not infinite time and compute, but like much more time and compute than you would have on the online setting. And there you can do much more processing of how you fuse the sensor data together. And that teacher network then can provide supervision about the features of what it saw for the networks in the online setting where you only get feature maps from the different vehicles in the scene. So it's kind of like a distillation of how you better fuse features together from different messages in the vicinity. And then another enhancement that this work proposes is I mentioned one of the limitations is domain, different domains for different autonomy systems. So one autonomy system might be doing point pillars, another one is using second or whatnot, or center point. And so you have to kind of merge features that are from very different training data and have a domain gap with each other into a shared representation. This does some type of domain adaptation to be able to combine feature maps from different autonomy systems together. And I'll note one thing is that like this is still assuming some of the like spatial intermediate representation. If you have like a autonomy system that's end-to-end that directly takes sensor data and outputs actuations, it might be much harder to kind of support this type of communication between different vehicles. And the other questions that I mentioned was also about compression. Like, how do I transmit the best data possible as efficiently as possible? For each of the fusion methods we mentioned, there are several ways of compressing the data. So for sensor data fusion, there's several methods. It's a whole field on LiDAR compression and image compression one could use to transmit the sensor data effectively. For output level compression, for bounding boxes and trajectories, it's already quite compact, but it might be an interesting direction for future work to consider how you might want to compress occupancy-based representations, which have become more promising potential direction to consider for autonomy. And then, of course, for feature compression, there's also a lot of work out there on compressing neural network feature maps, either through like convolution-based compression or some type of like matrix compression. Cool. And we talked about what type of stuff vehicles can communicate with each other, how to fuse the data. And now this other question that we talked about was, what types of vulnerabilities do you introduce when you introduce vehicle-to-vehicle communication in your self-driving system? And one of the things is that because you're getting new information, just like you have in multi-sensor fusion, you have more noise coming into your system as well. So examples of types of noise you might encounter is localization error between different vehicles. Each vehicle might have its own localization error of like a few centimeters maybe or more. Also orientation error. And when you try to aggregate messages from different viewpoints that are say 50 or 100 meters away from each other, that type of error can aggregate when you get into the shared coordinate space. So it's really important to be able to handle that, because if you have misaligned features or misaligned point clouds, it's much more noisier to understand what's happening in the scene. So this work proposes kind of like a learned type of ICP-based alignment of feature maps to allow for noise in the pose error. Also another issue of pose, not just localization error, but time delay errors. So different vehicles might have issues with their time synchronization or might see different points of view at different points in time. So you need to handle that as well accordingly. And also the possibility of adversarial attacks. And that leads into the next point for this talk, which is there's also options and possibilities of adversarial attacks in vehicle-to-vehicle communication. So one work proposes kind of like adding perturbations to the feature maps and seeing if those type of feature map perturbations, if you have like a infiltration in your network, if you can kind of cause the autonomous system to have failures. And similarly to the adversarial community, there's lots of work on doing these attacks and adding them as data augmentation to improve robustness. And then, of course, there's also not just attacks where you have a man in the middle in your network, but also what are kind of failure combinations of, given a particular scenario, which vehicles are intelligent and which ones are not, and where do I place them such that the vehicle-to-vehicle communication causes a failure in an autonomy system. So that's another interesting paper that's been proposed on adversarial scenes specifically for V2V. Awesome. So we've talked a lot about the different types of approaches for vehicle-to-vehicle communication, but just like any other field and topic in computer vision and robotics, it really matters how much data you have to be able to make progress. And in something like V2V, where it's kind of futuristic, it's much harder to get like real good data of what you need for tackling the problem. And similar to other data sets problems, you want really realistic data. You want to be able to have sensor diversity of different LiDARs, cameras, radars, et cetera, and on different vehicle platforms like cars and trucks and infrastructure or even drones. And you want to have a lot of scale to make performance effective and be able to benchmark your methods. And the other thing I'd mention is that for like V2V communication, you also want interesting configurations where you have different vehicles coming in different directions and interesting scenario configurations to create kind of the complexity you might expect in the real world in the future. Typically, like this is a kind of an unideal setting where each of these vehicles are just following one each other after another. You can't really do much V2V communication of new visibility of the scene in that type of setting. So we've compiled a table here of a lot of recent data sets that have been done in the community for V2V communication. Especially in the last few years, there's been a group that's been able to produce a lot of great data sets. You can see here that some of the things to look out for is if it's a simulated data set versus a real data set, what types of sensors are on the platform, and if it's infrastructure, also just intelligent vehicles included, types of classes, and the locations. For simulation-based data sets, we kind of showcase two here. We have one that's like kind of a data-driven based approach where you take real-world logs and you simulate the sensor data from different viewpoints within the scene itself. So you can have the realistic configurations you want and also have scalability and diversity of the scenes. But in this particular paper, for V2V sim, we only did this for LiDAR simulation, not for other sensors. But the other option is synthetic data sets with a game engine. You can generate much more sensor modalities in these past papers. You can fuse like LiDAR, camera, etc., and it's much more controllable. But you have a little bit less scale and diversity when you have a synthetic scenario versus real world scenario. Awesome. And then here's real world data sets that have been proposed recently. You can get diverse scenes, but because it's kind of hard to get so many vehicles in the same place that are intelligent, it's still a bit limited in the types of configurations you can get. Awesome. So in conclusion, we talked about different methods for vehicle-to-vehicle communication. There's the early fusion, intermediate fusion, and late fusion, and people are still working on trying to find the best balance and trade-off for performance. There's also work being done to improve the robustness of these systems and handle attacks, errors, and pose and time delay. And of course, we need new data sets that kind of push the performance of these methods so we can have more scale, more realism, and sensor heterogeneity in order to get the complexity we might see in the real world one day in the future. And some promising directions that I think might be interesting to pursue is peddling these types of different platforms from different companies, improving the memory and time bandwidth, continuing to push the performance of these self-driving vehicles to be real time, improving robustness, as well as most of the works that we've talked about so far have been mostly communicating bounding boxes and perception outputs. Maybe some works have also done prediction communication, but there's also like a huge area of work potentially in communicating outputs of the full autonomy system. Like, where am I going to go next? You can imagine like in, say, a four-way intersection. If you have enough vehicles in the scene, there's no need to have a stop signs. You just go, right? You can communicate what your plan is ahead of time. There might be less traffic jams this way as well. So kind of extending these works to not just be perception, but also full autonomy downstream task is also an interesting direction. Awesome. Thank you. Happy to take any questions.